Good morning. Good morning, everyone. Welcome to day 4 of the conference. And it's a beautiful day outside. We're going to be inside for most of it. But we have a great program today. And the first session is on time and consciousness. And we have 3 speakers. And the first speaker is a good friend of mine, Daniel Sheehan, a professor at the University of San Diego, a physicist. And he will be speaking on the broken arrow, time asymmetry, and retrocausation. Daniel.
Thank you, Stu. There are few ideas in Western civilization that carry so much weight as the concept of time. You have entire subdivisions in philosophy who are devoted to the problems associated with time. We have archaeology, we have history, and literature is replete with references to it. Like as the waves make toward the pebbled shores, so do our minutes hasten to their end, each changing place with that which goes before, and sequent toil our forward do contend. Tomorrow and tomorrow and tomorrow creeps in this petty pace from day to day until the last syllable of recorded time, and all our yesterdays have lighted fools the way to dusty death. Indeed, time is the river upon which we flow. It is the fire in which we burn. Well, in physics, we've been using time as an index of change for over 300 years. We have clocks now that are precise to within a few seconds over the age of the universe. With our telescopes, we can look back in time to the beginning of creation, and we can hack a single second down to a millionth of a billionth of a second. And yet, despite this, the concept of time, the phenomena of time, has now come under unprecedented kind of, how should I put it, scrutiny. There's somewhat of a crisis in physics. We don't know quite what time is, or even what direction it flows. This morning, Patricia Cyrus and I would like to present what time has to say about consciousness, or maybe more precisely, what consciousness can say about time. Now, before we begin, I'd like to do 3 things. First of all, I'd like to thank Stuart for the invitation he extended to Patricia and me to give a talk. And also we'd like to thank Abby for keeping everything on its rails. Patricia was unable to attend this meeting. She sends her regrets and best wishes. So I'll be presenting alone. And third, I'd like to note that Patricia and I are both probably what you'd call dualists, but on the other hand, for the purposes of conformity to the scientific consensus, we'll talk as if we are materialists in this talk. Okay. Now, the overview is straightforward. First, I'd like just to talk a little bit about time symmetry in physics, and then the arrows of time, and then talk about quantum models that admit retrocausal or reverse time properties. And finally, time and consciousness, and maybe the possibility for constructing a quantum oracle. All of the fundamental processes in physics possess what is called Cpt symmetry. This is one of the great achievements of the 20th century physics. And what Cpt stands for is shorthand for charge conjugation, parity transformation, and time reversal. And what that means is this. If you take any fundamental process, like the one depicted here, which is an electron-positron annihilation, forming a gamma ray, which then breaks off into a quark-antiquark pair, and one of which spins off a gluon. If you take any of these fundamental processes that make up the universe and go through charge conjugation, which means to turn matter into antimatter or swap the charges, and then go through parity transformation, which amounts to a mirror reflection, and then finally time reversal, you will find that you get an allowed transition or an allowed process. So nature seems to like this particular symmetry. The fundamental laws of physics that we use are what are called time symmetric. They possess time reversal symmetry. So if you look at any of the basic equations, the fundamental equations of physics, Newton's laws, Maxwell's electrodynamics, Einstein's equations, Schrodinger equation from quantum mechanics, you'll find that if you take time as a positive quantity and reverse its sign with the other appropriate conjugations, like in quantum mechanics, one finds you get the same equation back. So for instance, if you take Newton's second law, force equals ma, and you have mass times the second derivative of position, this is the equation we normally use, but if you were to put in negative time, you will find that in the denominator of the derivative, the negative time is squared, and so it becomes positive again, and you get the same equation out. What this means in a practical sense is that for every positive time solution you get in physics from the fundamental equation, a solution that propagates forward in time, you also have an equation that propagates backward in time. Now, these are normally ignored in physical situations, but they exist. And you can see this evidently in such things as the swinging of a pendulum. So if you take this watch and swing it back and forth, if I were to reverse the time, it looks the same. So here I'm going to reverse the time, there it goes, positive time, negative time, and it doesn't matter. Both solutions, you have a time symmetry in fundamental processes. You also see it in such things as, let's say, a ball, which is thrown up in the air. If I take a ball, throw it up, you get a parabolic flight, but if you were to reverse that trajectory, you would get the exact same one. So whether you go time forward or time backward, nature really doesn't seem to care. And in terms of looking at things in terms of causation, well, let's take a simple example. Let's say we were to look at a ball rolling down a hill. In the present moment, it's in the middle of the hill, rolling. You could say that the reason why it's rolling down the hill and is found in the present in the middle of the hill is because in the past it was at the top of the hill. And if you were to assume that, then you would talk about a causal relationship between the past and the present. On the other hand, it's equally valid to say that the reason why the ball is in the middle of the hill right now is because it will, in the future, be at the bottom of the hill. And you can run the future backwards and get the present. So either way, you can think of causal or retrocausal as being kind of mirror twins of each other. Now, this is true of the fundamental equations associated with physics, but in everyday life, we don't see that at all. We see time going in one direction. So although the fundamental equations are time symmetric, nature itself appears to be time asymmetric and irreversible. So in the left panel, you see a glass shattering with a bullet perhaps passing through it. The middle, a cracked egg. You can't unscramble an omelet. Or in the third, an explosion. And what the underlying cause of this, or I should say the law underwriting all of this, is the second law of thermodynamics. So let's just do a simple demonstration of reversible versus irreversible. Here I have a carafe with a little bit of water in it, and a second one with some cranberry juice in it. Now, if I pour the cranberry juice into the water, I get a mess, but I get a solution, obviously. Now, it is entirely possible within the fundamental laws of physics for all of these molecules to segregate themselves, for all the cranberry juice molecules to go to the top half of the jug, and all of the water molecules to go to the bottom. This is entirely possible within the fundamental laws of physics, but you never see this happen. You could wait 1 million, billion, trillion, quadrillion, quintillion times the age of the universe, and the probability of it happening is virtually zero. And this is because of the second law of thermodynamics. The probability for it to occur is virtually nil. So we see a progression of time due to the second law. And this is one of several arrows that have been identified. The arrow of time was coined by Arthur Eddington in the late 1920s, and it indicates that we see a progression of time in one direction, although the underlying equations appear to be time symmetric. And there are a number of possible arrows. The ones that I think are maybe most pertinent at the moment would be the cosmological arrow. This is the one that is tied to the expansion of the universe. After all, the universe could be expanding or it could be contracting, but it happens to be expanding, and that gives an overall arrow to the cosmos. Kaon decay refers to certain CP or charge parity violating decays which also imply time reversal asymmetry. And these are tied apparently to the fact that that matter predominates over antimatter in the universe. So in a way, we wouldn't be talking here at all probably without Kaon decay arrow. And then the one that affects us most on an everyday basis is the thermodynamic arrow, the one that allows entropy or disorder, prescribes that to increase, but never decrease. The radiation and psychological arrows are probably tied to this. After all, we are electrochemical machines if you're a pure materialist, and therefore subject to the thermodynamic arrow. So the classical equations of physics are time symmetric, which means reversible. On the other hand, classical reality is not. It's irreversible, and this is probably tied on an everyday basis to the second law. But even this arrow has come under question. There have been, over the last 25 or 30 years, kind of a quiet renaissance in thermodynamics. There are a number of groups around the world who have posed challenges to this law. There have been 3 to 4 dozen that have entered the mainstream scientific literature since 1995, both experimental and theoretical. International conferences have been held for 20 years now. A Springer monograph was published in 2005 by Vada Capek and myself concerning these arrows. And as of now, there are several groups in the world which claim to have experimental evidence for second law breakdown. One in Colorado, Garrett Medell, dealing with Casimir cavities, asymmetrically constructed with respect to diodes. One that made a splash a couple of years ago, University of Arkansas, Paul Thibodeau, with graphene membranes. James Lee, Old Dominion University in Virginia, and then the experiments at the University of San Diego dealing with epicatalysis and thermal batteries. So this arrow may be broken. In quantum mechanics, well, this is another arrow that is broken in a different sense. The formalism of quantum mechanics, much like that of classical mechanics, is formally time symmetric. And in fact, there are a number of retrocausal models which explicitly use retrocausal or reverse time effects in order to gain the results. These date back about 70 years. And the 2 of the most famous are the two-state vector formalism from 1964 by R. Hameroff, Bergman, and Leibowitz, and the transactional interpretation, which was posited and forwarded by John Kramer in 1986. And I'd be remiss not to note that the next speaker, Paul Davies, actually did some very beautiful work in the early 1970s with time-symmetric formalisms of electrodynamics. So how does retrocausation help? I mean, it seems counterintuitive, but how does it help the situation in physics? Well, first and maybe and foremost, it respects the time symmetry of the equations that we're using. It honors the formalism and does not ignore those solutions. Now, 100 years ago, there was an argument, kind of a semi-public argument between Ritz and Einstein over this issue. Ritz claimed there needed to be a law of physics that explicitly said that only time-forward solutions are allowed. And Einstein said, no, you can't do that. The mathematics doesn't justify that. There is no law of physics that says that time only goes in one direction. So simply to respect the time symmetry, I think, is just good practice in general. Also, it can be shown to restore relativistic locality to entangled states. Some of the more, and things like EPR paradoxes are easily explained using retrocausation. Many particle wave functions can be reduced to single particle wave functions, so one doesn't have to deal with high dimensional configuration space in quantum mechanics in some of these models. It also makes the wave function ontologically real. Now, many of you, or probably most of you, are aware that in the Copenhagen interpretation, the original interpretation of quantum mechanics, the wave function was considered only to be epistemic. In other words, something that deals with our knowledge of nature. But the wave function does not describe anything real. In some of these retrocausal models, you can treat the wave function as something that's actually real, and that's a real benefit. From this, you can derive the Born rule, which is an ad hoc assumption in Copenhagen quantum mechanics, but you can derive explicitly once you start taking retrocausation into account. Also, quantum computing, the speed up that's associated with quantum computing has been tied to retrocausation by some beautiful work done by Giuseppe Casagnoli in recent years. Finally, and maybe most importantly, the mysticism and the paradoxes associated with quantum mechanics can be much more easily resolved and more aesthetically resolved if one invokes retrocausation. For instance, the mysticism and the mystery and the, how should I say, the mystique surrounding quantum mechanics is largely tied to the paradoxes. But once you involve retrocausation, you can take care of things like the EPR paradox, Schrödinger cat with the ontological wave function, Wheeler's delayed choice, quantum erasers, Wigner's friends, Einstein's bubble, interaction-free measurements. Time symmetry, or allowing for retrocausation, gives you entirely, gives you a new and simple way to look at nature, and for only the benefit, for only the cost of honoring the equations that we originally have. One of the models which is most heuristically interesting is the transactional model developed by John Kramer at the University of Washington. It's based on the Wheeler-Feynman electrodynamics model from 1945. In it, he posits two kinds of wave functions, which are normally found in quantum mechanics, and he interprets them in a particular way. Psi, which is known as what he would call the retarded wave, the one that propagates from past to future. It would be causal in nature. The second one would be psi star. It's called the advanced wave, the one that propagates from the future into the past, and it would be retrocausal. What the present amounts to is a handshake agreement between the future wave function and the past wave function, or the advanced and retarded potentials, or waves, to create present reality. So let's look at one particular case of an application of the transactional model. About a month ago in the journal Nature, it was reported that the farthest known star had been observed. The star was nicknamed Earendel, which is Old English for morning star, and it is located at a distance of 12.9 billion light years from Earth. It was observed due to gravitational lensing of a distant galaxy, and so its brightness was increased by the lensing effect by a factor of 1,000, which allowed it to be observed. So let's see how the Hubble Space Telescope, which saw it, would have seen it using the transactional model. So let's begin down here in the lower right. This is a space-time diagram, vertical axis corresponding to time, and the horizontal axis corresponding to space. So the star Earendel then is located at a distance of 12.9 billion light years, and the light that was emitted from the surface of that star 12.9 billion years ago, time is indicated by here, that particular photon was launched in a pretty much arbitrary direction. You can't really ask where it was launched, in which direction it was launched. It was just launched. And this wave expanded through space. Its wave function expanded through space. And then maybe a year ago, when it entered the Hubble Space Telescope and landed on the photodetector. And at that point, it made what is called an offer wave. That is the psi going forward in time along the light cone, right here, traversing up to the Hubble Space Telescope. A response wave was launched backward in time by the Hubble Space Telescope, and that would be psi star, moving backward in time. And then, once this connection was made between the offer and response wave, a stochastic choice was made. It was, if these were in phase, if everything looked like it was aligned, then a transaction was conducted. And it was repeated until completion, and energy and angular momentum and linear momentum were exchanged. And once that happened, you would have maybe something akin to the bing that Stuart often talks about. You have a moment of reality. And this is the quantum handshake. And this happens countless times on an everyday basis inside your body in chemical reactions. You would have these transitions occurring in molar quantities on picosecond timescales. On the other hand, the handshake would take 6 minutes to occur. Let's say photon emitted by the sun would take 6 minutes to get here, and then have to decide whether it's going to make a transition and appear on Earth, so to speak. For Arundel, it took almost 13 billion years to make that decision. So our present reality then can be thought of as handshake agreements between past, which can be very short in time or very long in time, and the future. You can also explain away most of the kind of mysterious paradoxes in quantum mechanics. John Cramer claims that all of the paradoxes in quantum mechanics can be easily resolved from the transactional approach, and this appears to be the case. So the famous EPR, Einstein-Podolsky-Rosen paradox, has to do with what's called the spooky action at a distance. So let's say you had, this is based on the Friedman-Clauser experiments from the early 1970s. You have a polarization entangled two-photon source, which means you have 2 photons created from a single source, in which case, in principle, the polarization of each photon leaving the source is indeterminate and entangled with the other. Well, in this model, you would have the source, and you would have your 2 measurements devices, and in principle, these measurement devices could be space-time separated, which means their separation is sufficiently large that that during the times of the 2 measurements, there's insufficient time for a light signal to connect them. So these would be considered non-local. In transactional interpretation, you would assume, for instance, that if the polarization is of your detector is, let's say, in left polarization, your offer wave would be left polarized, and then I would go to the source. The source would come from the source to the detector. The detector would send back a confirmation wave, and if there was an agreement there, and also an agreement here between this detector and this photon, everything would be set right. You would have time forward and time reverse solutions going simultaneously, checking out the boundary conditions. If all the boundary conditions match up, then you can have your Bing, and you can have measurements of these polarizations. Other paradoxes involving time are similarly easily handled this way. So let's kind of take a look at between Arundel and EPR. If we truly believe that the future and the past and the present are all connected to each other through these transactions, both locally and non-locally, as in EPR configurations, then we live in a vast network of both causal and retrocausal interactions, and all of these come together under being preserved and kind of orchestrated by the laws of physics, under the underlying laws, to create our reality. Now, when it comes to consciousness, retrocausation can also play a role. I will not discuss it here. This has been discussed far too long and with kind of inconclusive results, at least from some people's points of view. The famous Libet experiments from the 1960s, these can be addressed through retrocausation as well. But in particular, precognition, presentiment, and remote viewing present an interesting case in possible retrocausation. Now, precognition exists in classical reality. It's been reported throughout history. It may confer survival advantages to know a little bit about the future, to know where you might find food, how you might avoid predators, and so on. It is a rare but testable phenomena in the laboratory, but it demonstrates a connection between the present and the future via consciousness. Many experiments have been conducted over the last 40 years in the laboratory to look for both presentiment and remote viewing. The one that I probably don't have time to discuss, unless maybe during questioning, would be the Graf-Cyrus experiments. Patricia Cyrus was involved in these. And the way one can handle precognition, one way in which it can be handled, and there's more than one, of course, but this is one way and a rather parsimonious way, via the transactional approach, is to explain it the following way. Let's consider the viewer who's having a precognitive viewing to be in the present at time equals 0 and x equals 0 in the space-time diagram. And the future self, the same person in the future sending back signals, an advance wave from the future, and then an offer wave from the present. And if there is an alignment between these two, you can have a transaction, in which case a future event can have an effect on the observer. And in fact, the observer, the future observer, can have an effect on herself in the past. And this could account for precognition. Now, there are various caveats associated with this, and models are being built, one of which is indicated in the lower right of this figure. So precognition. Patricia and I believe it is the most striking evidence of possible retrocausality in classical reality. And it is also, we believe, the best evidence for the quantum nature of the brain, the mind, consciousness, however you want to conceive of it. Because classical reality cannot accommodate retrocausation, largely due to the second law of thermodynamics, but quantum mechanics can. Some quantum experiments, both in the laboratory and with human subjects, can be interpreted as retrocausal. Precognition can be interpreted as retrocausal, and if so, precognition strongly suggests that the mind, in some sense, is quantum mechanical in nature. We take this as a prima facie evidence for the quantum nature of the mind. Now, a couple of days ago, Christoph Koch claimed that, well, quantum mechanics can't really occur in the brain. Well, in light of the evidence for retrocausation at this point from precognition, I would say that that's a lot like saying, I've just traveled to St. Louis, and someone then calling me and telling me, you can't get to St. Louis when I'm already there. It's just a question of whether, it's not a question of if there is quantum nature of the brain, I believe right now. It's a question of how it's attained. Now, looking at it in terms of fundamental properties of temperature and decoherence are fine, but they do not exhaust the quantum, how should I put it, the quantum resources available. And particularly with studies in quantum information, there are lots of other ways in which the mind or the brain could possibly preserve quantum natures, things like quantum discord, which allows the preservation of quantum correlations even in light of heat and standard decoherence. Quantum discord survives much longer than entangled states in hot environments. Or if one considers thoughts, for instance, to be some quantum wave functions in some sort of vast Hilbert space, you could consider something as intricate as the brain as creating memories and thoughts which are so unique that they would constitute something like a decoherence-free subspace, which would be protected against decoherence. So I think there are plenty of resources in quantum mechanics to continue to address the issue of the quantum nature of the mind, and precognition, I think, is very strong evidence for it. The evidence of it is so strong that several colleagues of mine and I, including Julia Mossbridge here at the conference, and I and others, we are hosting a conference this coming summer in which we're bringing together quantum scientists, philosophers, science fiction writers, anyone who maybe can address this field, to actually think about actually developing a machine that can send information back from the future into the present. This conference is Quantum Time Machines, Design and Development, and it will be hosted at the University of San Diego this coming July. So in summary, physical laws are time symmetric, and classical reality, though, seems to be time asymmetric due to the second law. But the second law itself, although it works beautifully well, appears to have certain loopholes. So that particular arrow may be a bit blunted now. Quantum reality formally should be time symmetric, and there's good experimental support, both in standard laboratories and in human studies, for retrocausation, one of which, of course, is precognition. Precognition might be explainable using both thermodynamics and quantum formalism. And this suggests that the mind and consciousness are probably quantum mechanical in some respects. And we hope that perhaps quantum oracles may be developed in order to look into this time issue more carefully. Patricia and I believe that it's time to take time seriously. Look at the formalism, honor it, and also honor experiments, which seem to indicate reverse causation, because this leads both into a deeper insight of the universe, but also into consciousness. Thank you.
Okay, we have time for a few questions while we set up for the next speaker. Please line up.
All right, let's see if I can phrase this right. So if we use Ellendar as an example, you're saying that the timeline begins from the moment that photon leaves Ellendar.
Yes.
And one timeline is the future timeline, moving back in time.
Correct. Yes.
Initiates from the is then initiated 3.5 billion years into the future, and the its opposing line, and it crosses over that same distance from the
Yes, continue. Yes, that's correct.
So it, and at the same time, once they intersect at the present, it's as if that distance in time didn't exist at all.
So maybe I can kind of short circuit this question, because I think what you're hinting at, and it's a good observation, is that this connection is done in an atemporal sense. It's moving along the light cone in both directions, and so this connection is done instantaneously between the two. So it's not like you have to wait for 12 billion years in one direction and 12 billion back. No, that's not the case.
Right.
Okay.
Thank you.
Okay, thank you.
So you can explain from this model why precognition happens, but can you explain why it's so rare? Why if we have time symmetry in the laws of physics, why would precognition not be commonplace?
Okay, I think there are multiple reasons. It's a good question. I think there are multiple reasons for that. One of which is that I believe the second law probably obscures it in many cases. And also, from an evolutionary point of view, if you look at it as a resource that human beings use, or animals and human beings use, knowing too much about the future is not necessarily a good thing. Maybe a little bit of information is good, but if you're always spending your life in the future, you get eaten by the lion in the present. So there are various ways of looking at that.
May not be that rare, it might be subconscious.
Yeah, and Stu's right. I mean, it could be happening and at a low level all the time and just not being noticed. Yeah.
Hi. Can you elaborate more about the precognition experiments? Because as far as I know, and I checked it a bit, all those experiments does not meet the strict conditions for a proper scientific results. For example,
Yes.
Redding, his results are
That's right.
right. So they are not statistically significant. You cannot distinguish between them and noise. So what?
I'm sorry, which experiments can't be distinguished between that and noise?
The Dean Redding experiment.
Well, there are lots of experiments. You can do meta-analyses if you wish. The ones I didn't have time to present, ones done by Patricia Cyrus and Dale Graff, are stunning. These are so far out of the noise in terms of normal interpretation, I doubt you can make a credible argument against them. So I think you can't look at one experiment necessarily. There are lots of experiments. The Darrell Bem experiments from 2011, 2012, where we did a suite of them showing retrocausal behaviors, I think stand up statistically quite well as well as many others.
Great, I'll have a look.
Thank you.
Thanks, Dan. Great presentation. Just a question. So if there's information being sent back to us from the future, does that imply that the future is predetermined? I was just wondering if you could comment on determinism and free will.
I'm kind of agnostic about that, I guess. It might be interpreted that way. I think there might be ways around that as well. I live my life as if I have free will, and as I've mentioned before, I mean, I follow Elie Wiesel's, the writer's prescription for that. You must believe in free will. Okay. You have no choice. Okay.
Last question.
Yeah.
Sorry.
Okay.
We're going to leave time at the end, so.
Great presentation, Daniel. Thank you.
Sure.
So just a quick, could you elaborate on your perspective on, in the transactional model, you have these signals that you can abstract away and analyze the time forward and the time backwards.
Yes.
Is there a meta time that happens within?
Yeah, that's the way Kramer described it is he calls it pseudo time. Yes, where it's kind of a frame of reference where really no time passes between these interactions, so you don't have to wait these.
So can you elaborate more on your perspective on that, and does that add to the structure of quantum mechanics, or just say a little bit more about that?
That's a good question. I think well, if you take the interpretation seriously, yeah, it certainly would. That's right. Yeah, and it should be addressed. Okay.
Thank you, Daniel. Let's give him a round of applause. That was great. Okay, our next speaker is a very eminent, well-known physicist and author of, how many books now? 32 books. And the most recent one, I believe, is called What's Eating the Universe? And I want to find out what is, as we all should. And he's also the head of the Beyond Center at Arizona State University up the road here in Arizona. He's widely known for many things, including some of the things that Daniel mentioned. A round of applause, please, for Paul Davies.
Thank you so much, Stuart. Thank you for inviting me to this meeting. I have a picture of you here with a frozen thought, and it might be a profound insight into the nature of consciousness, or it might be, where can I get lunch? But I think everybody would agree that time is the most fundamental aspect of our experience. Even under conditions of sensory deprivation, we are aware of the succession of our own thoughts. And usually this is cast in the language of the flow of time or the passage of time. And because it's so profound, it has permeated not just science, but all of the humanities. And so we see many references in literature, many metaphors about the flow of time, the river of time, or a very ancient metaphor from the poet Andrew Marvell, but up my back I always hear time's winged chariot hurrying near. And he penned those words just a few years before Isaac Newton captured that concept in his famous Principia, absolute time flowing equably without relation to anything external. So the notion that time passes or flows would normally never be challenged by any individual who didn't specially take an interest in the nature of time. It just is something that goes with our own existence and our own sense of identity. And so we don't find anything remarkable about these statements. What is remarkable is that they are in fact nonsense. Time doesn't pass. The flow of time is an illusion, and that's the central theme of my talk this morning. I was going to make the quip that in a session on the nature of time, we're in an auditorium with no clock, but now I'm standing here at the front, I see that there is a digital clock here, but it's not moving. So I'm a little bit helpless to know when I should stop speaking, but I will endeavor to estimate, but somebody give me a 5-minute warning. Anyway, the idea that time doesn't pass won't come as a surprise to any philosophers here, because it's long been part of contemporary philosophy. Famous paper by Donald Williams, The Myth of Passage, dates from 1951. But this idea that there's some confusion about the nature of time having to do with its passage goes back a long time before that. Now, I want to disabuse you of one misconception right at the start, because you will see many magazine articles, websites, lecture titles, and so on, claiming that time might not exist. This seems to be a rather popular thing to say at the moment, that time is an illusion. I'm not saying that time does not exist. Time does exist. It's something that we measure using clocks. Time exists, but the flow of time, I'm saying, is indeed an illusion. So don't think I'm trying to abolish time. I should say that there is an entire area of inquiry, quantum cosmology, applies quantum mechanics to the universe as a whole, in which time appears as a parameter, and it can be eliminated by reformulating the theory where another variable plays the role of a clock. Could be the size of the universe, for example. As we heard from the previous speaker, the universe is expanding, so you can tell the time just by measuring the size of the universe. So you could, in a fundamental theory of quantum cosmology, do away with the time parameter altogether. That's all fascinating stuff, controversial, and I'm not talking about that here. That's not what I am trying to say. So that's, forget that one. Well, let's just go right back to basics and ask the question, what is time? This is my favorite definition. Time is just one damn thing after another. But we've got to be a little bit more precise about that. So the mystery of time really goes back into ancient history, and Augustine was famous for his deliberations on the nature of time, and sort of captured that idea that we all know what time is from our own personal experience, but as soon as we come to discuss it or define it or debate it, we get confused. And so what I'm trying to do today is to dispel some of that confusion. So that's Augustine's view. Put simply, time is the duration between events, and that's something we measure with clocks. Clocks do not measure the flow of time. People often say that. You know, what about a clock? Doesn't that measure the flow of time? No, clocks measure the duration between events, just as a ruler measures the distance between 2 points. And indeed, as Einstein told us back in 1905, we cannot separate the nature of time from the nature of space. We combine them together into a unified space-time. And that's a really important aspect of what I'm going to say, and fortunately, Daniel Sheehan in his beautiful talk explained some of these things, so I'm not going to dwell too much on it, but he did show you this light cone. So for those of you who are not physicists, let me just take you through this very briefly. The way in which we like to represent space-time, this unified four-dimensional entity, I can't draw 4 dimensions on a flat sheet, so we're going to get rid of a couple of dimensions of space, and what you see on the left is time running vertically and space running horizontally, and because of the theory of relativity, we can't separate the one from the other. What happens to the one affects what happens to the other. And the blue lines are the paths of light rays or photons in this system of units, where the distance is measured in meters, or years if you like, and time is measured, say, in years, distance in light years, and so that's at 45 degrees. And so the theory of relativity says that events that occur in the blue region can causally affect each other, but those that are outside of the blue region cannot. And if we add an extra dimension of space, then we can sort of rotate that triangle and get a cone. And so that, we call that the light cone, or sometimes the null cone, because the four-dimensional distance along it is 0. And so that's just sort of the basic geometry. And you don't need to understand the technical details of this. The point of showing it is that physicists will represent space and time as this single entity. It's sometimes called block time, because time is, as it were, all there. You'll see that curious wiggly arrow saying present. So what's that? Well, I'm going to come to that in a moment, but ignore it for now. The point is that we can look at space-time like a map being unfurled. So just as you have a map of the landscape, you can unfurl it, there it is, all at once. So we can have a map of the timescape, there it is, all at once. So it's the block time or timescape. And that's central to this idea that time cannot pass. or doesn't pass. And Einstein was aware of this right back at the beginning. He said the distinction between past, present, and future is only a stubbornly persistent illusion. He wrote that in a letter to the widow of a friend of his, Michel Bessot. Whether that was any consolation, I don't know. It seems a little bit brutal to say, well, you know, if you're a physicist, what does it matter? He's gone, but he was there in the past. Hermann Weyl, rather more sensitively, said this about the same time, the world simply is, it does not happen. Only to the gaze of my consciousness, crawling up the lifeline of my body, does the world fleetingly come to life. So the idea of this timescape or block time is central to the way physicists think about the world. It's just there. And if you say, well, what about the present moment? Isn't that a special thing? How is that defined? It's not defined at all. It's not there in physics. There's no law of physics that tells you this is the present. It simply doesn't make an appearance. Any moment of time can be considered the present moment, doesn't have any significance. And the reason it has no significance is because if you ask the question, let's take now, okay, well that just was now, and ask the question, well, what's happening on Mars now? And that seems like a well-defined question. Well, we could, you know, the satellites there, they could tell us and all the rest of it. But it turns out that that question is ambiguous because the notion of simultaneity, the notion of the same moment on Mars as now, as Einstein showed all those years ago, is ill-defined. It depends on your reference frame. So we could say, well, sitting here in this particular reference frame, there is an event on Mars that is happening now. But if somebody is zooming through the solar system in a rocket at half the speed of light, it will be a different event. So what is happening now is ill-defined. It's not possible to say throughout the universe that there is a present moment. And so because there's no universal present, no simultaneity, you have to consider time as extended in this block-like manner. So I'm sort of belaboring this point, but it's a very fundamental one, completely familiar to anybody who knows special relativity, but still comes as a shock to some people. So time does not flow. A lot of people say, well, of course it flows. Isn't that what clocks measure? Well, it asks the question, what is the speed of time? If time flows or moves or changes or passes, how fast does it pass? I can tell you the answer. It's 1 second per second. This is not a profound insight. It is just a tautology. When we talk about the speed of something, you can talk about the speed of a car relative to the road, and what you're talking about is how far does it move in space in an interval of time. But you can't say how far does time move in an interval of time. It just doesn't make any sense. So what I want to argue is that our illusion of the passage of time has to do not with the nature of time itself, but with the nature of consciousness, with the nature of the self. And this brings me to just mention briefly what is the speed of thought. Now that is something that has a definition, and there's this famous quip by the British Prime Minister Harold Macmillan about Foster Dulles, he of the airport, Secretary of State under Eisenhower. His speech was slow, but it easily kept pace with his thoughts. So we would be aware of the fact, and Miroslav Holub wrote this book called The Dimension of the Present Moment, and it's a very interesting subject. It's just a little digression, because if you think about a pianist, playing the piano, that's incredible. They must be thinking really fast that this middle finger has to go on that key at that moment, and it's all happening so quickly. Got really fast thoughts. But of course, they're not thinking it. Same thing with a tennis player. The ball is moving much faster than the speed of thought, and the tennis player makes the appropriate return, not because they're thinking, well, I'm computing the trajectory and I need to step to the right and so on. You do that if you play pickleball, which I've been doing recently. Then, the ball is going so slowly that you think, oh, no, here we go. But not with championship tennis, and so there are many things that we do which are faster than the speed of thought. But nevertheless, we do have thoughts, and they do lumber along at a certain speed, and so it's meaningful to talk about speed of thought, but not the speed of time. And so the central message is that the standard picture, the myth of passage, is that I am a fixed entity. It's me, it's Paul Davies, I'm the same person as when I was born, and the world is changing around me moment by moment. And sometimes people say, no, it's not the world that's changing, it's time changing or passing. But what I'm saying is that time is just all there, it's the timescape, it's a fixed part of nature, but it's me, it's I change, I'm the change. This was not lost on Lewis Carroll, who in Alice in Wonderland says, well, Alice says, I could tell you my adventures beginning from this morning, said Alice a little timidly, but it's no use going back to yesterday because I was a different person then, which of course sums it up. We change from day to day, indeed from moment to moment, but not by much. And because of memory, we have this illusion of conserved selves. Now, the technical way of expressing this is in terms of a quantity called mutual information. Let me just explain very briefly what that means. If I have a system over here, a certain amount of information to describe it, and a system over there, and a certain amount of information to describe that, if there's some correlation between these two, the sum is less, the whole is less than the sum of its parts, because knowing something about this tells me something about that. And the amount of overlap in the information space between these two is called the mutual information. And so if we take Paul Davies today, Paul Davies yesterday, slightly different, but an awful lot of mutual information, an awful lot of things in my memory, in my mind, in my brain state, and so on would be in common. And so it's very tempting to think, well, it's just I'm the same person, but the world has changed around me. But that's not true. It's I'm a different person. So you have a dog coming to listen to my talk. And I often think about, dogs that might sit around and discuss the canine condition or something of that sort. Are they concerned about these issues in the same way as us? If so, I'd be interested to hear from our canine friend. Look, I have to tell you, I'm sorry, when I give lectures, it always reminds me of things. A book I was writing 3 or 4 years ago called The Demon in the Machine. It's about the nature of life, and I was talking about unpredictability. I was writing literally on the beach in Sydney. I was sitting there with the laptop open on my lap, sitting on the sand, beautiful winter day. And suddenly, as I was typing, a dog ran over the keyboard. And this was a disaster because the sand got into the keys. And so I was just very confused. I was sand and eventually restored it. And I sat down and I thought, well, I wonder what the dog had to say about this. And it was blah, blah, blah. So I kept it in the book as a footnote in case one day we learn that there is something profound going on in the canine mind. Anyway, this really is a digression. So where was I? Yes. So a lot of mutual information, but we change from one day to the next. So that is why I call time an illusion. And there is an analogy which I like to use from time to time, which I think makes the point rather well. And this is the illusion of the rotating universe. Now, I was going to demonstrate this to you personally, but my wife cautioned me against it. So this is a ballerina doing a pirouette. Now, if any of you do that, you'll know if you twirl around and then stop, you have this overwhelming sense that the universe is rotating. And you think, I live in a rotating universe. But then you can sort of rationalize it and see that, no, it's not the universe that's rotating, it's something in my inner ear that is rotating. And so that's why we would say it's an illusion of a rotating universe. In the same way, the illusion of the passage of time will have something to do with the laying down of memories moment by moment. So as I've said, our selves change slightly, and that gives us the illusion of motion, which is not really there. Now, am I saying that there's no arrow of time in the world? We've just had a wonderful talk about the nature of the arrow of time, and I'm absolutely not saying that. The world is asymmetric in time. my first book was on that very topic, written too many years ago that I dare to tell you. And it's about the fact that physical processes all around us have this pervasive directionality towards greater entropy or disorder. So if you open the Great Book of Nature, around about page 2, you'll find the Second Law of Thermodynamics. We just heard all about it. It tells us that order tends to give way to disorder. And because Daniel explained it so well, I'm just going to rush through a few examples, get on some other points. This is one example of a disordering effect. Why am I showing this near Bologna? Well, I happened to be giving a lecture on the subject near Bologna all those years ago. The egg is another famous example. It topples off your kitchen surface, splat, there it is. You can't reassemble it. So we've heard about this. Another one I quite like, here is a snow person, as we should say these days, next to a fire. We never observe the snow person getting bigger and the fire getting cooler. The heat is always transferred the other way, and that gives us this pervasive arrow of time pointing from past to future. So for those of you that do feel muddled, that's probably because the arrow metaphor is a muddled metaphor, and I just want to make this absolutely explicit because people really do get hung up on these issues. One way in which we can think of an arrow is fired from a bow. It's flying through the air. It describes motion, a vector. It's in a particular direction and at a particular speed. That's one use of the arrow metaphor. But we use arrows in other ways. For example, on a compass needle, the arrow points north. Or a weather vane, it points in the direction the wind is blowing. And that doesn't mean that if you're holding a compass with the red bit pointing north, that you're moving north. It doesn't tell you which way you're moving. It's a directionality. It's not a motion. And when I use the term times arrow, when anybody uses the term times arrow, that it should be used in the sense of the compass needle. It points in a particular direction. So it's meaningful to talk about future events and past events. It's not meaningful to talk about the future, because as I've told you, there is no privilege now, no particular special moment. But events that lie in the future of other events, that time ordering is fine, so long as they're within the light cone. If they're outside the light cone, there's ambiguity in the time order. Depends on your reference frame. So this is a complicated way of showing all this. Let me just say, I'm trying to make the point that nothing really changes, but there is an arrow. The arrow is the arrow of entropy. It's pointing in a particular direction. We can call that the future. That's a definition. And what we see on the left are a sequence of mental states. And that might be you at 9 o'clock and you at 10 o'clock and you at 11 o'clock or whatever it can be. Subdivided down to, as I've explained, maybe, a millisecond or something. We can't go much below that. And then there are states of the world that correlate with that. So there's some particular mental state that correlates with a particular state of the world which is described by a particular state of a clock. Say T1, and then later on the clock shows a different position, T2, and after that a different position, T3. And these correlations simply show that as the world, from moment to moment, we have different states of the world. From moment to moment, we have different mental states that correlate with them. Nothing's changing, flowing, moving. It's just all there. And later mental states correlate with later states of the world. And there will be states, your mental states, I hope, in the future of this lecture. And they'll be correlated with slightly different states of the world in the future of this lecture and different positions of the hands on the clock. And that's all there is. We in daily life, we find it very cumbersome to talk this way. It's much easier to say, we can go out for dinner when the weekend comes along. People often use that expression. Where's it coming from? It's here. I can see the weekend coming. It's just absurd, of course, when you stop to think about it. The weekend doesn't come along. But to say at clock time weekend or something, Paul Davies at that time, will be in a restaurant or something. We just don't want to talk that way. But because it's so familiar to talk in terms of this flowing or passing time, we tend to think it's real, but it's not. Now, how much time have I got? So this thing is counting down. All right, but it started late. Should I finish? All right, I'm just, okay, 5 minutes. I do want to make some, and Roger is speaking next, is that right? Yeah, so I do want to make some connection with that. And by simply saying that the origin of this time asymmetry, as we've known for many years, is connected to cosmology. It is a cosmological problem. And there's a very obvious way of seeing that. This is the fuel bill for the sun I computed a few years ago. Energy's gone up a bit, so you should probably double that. This is basically what the sun is churning out into space every second. And of course, most of it's wasted. It just goes off into the depths of space. Some hits the Earth and does some good, drives life and so on. But basically, it can't go on forever. The sun will eventually burn out and die. And that's true of all stars and true of all processes in the universe. They run down. Their source of energy gets depleted. And this gloomy conclusion was drawn as long ago as 1852 by Lord Kelvin, who coined the term the heat death of the universe, that the entire universe is on this one-way slide to a state of maximum entropy and disorder. And so that raises the question of how the universe started out. This was before the Big Bang Theory. Now we think the universe began with a Big Bang. How it started out, and it clearly must have started out in a more ordered state than now. And that's a whole lecture that I could give, but I simply don't have the time. I just want to make the point that the key to understanding all this is gravitation, that the universe started out in a state where the matter was close to thermodynamic equilibrium, but the gravitational field was very far from equilibrium. And this subject has been made famous by our next speaker, Roger Penrose, who many years ago quantified the degree of specialness that the smooth early conditions of the universe, the gravitational simplicity of the early universe, represent. And you can do that using Stephen Hawking's famous formula for the entropy of a black hole. I'm not going to talk you through this. You'll either know this formula or not. If you don't know it, then it's on the gravestone in Westminster Abbey, where Hawking's remains were placed. And so you can go there and see it. But most of those terms there you can ignore. The only one that really matters is the M. And if you put in the mass of the universe, as Roger did all those years ago, you get an entropy, this big number, 10 to the 123, 1 followed by 123 zeros. And if you turn that into a probability, and for WMAP, read Planck now, for those who know about these things, how unlikely were the smooth conditions at the time that satellites can discern from the early universe. We have to exponentiate that, so it's roughly 10 to the power, unlikely, 10 to the power minus 10 to the 123. That means you write down 1 followed by 123 zeros, and then that's the power. So it's 1 followed by 1 followed by, okay, so I think you can get the point. It's a very small number, so it seems like a near miracle. And the whole subject of the connection between cosmology and the arrow of time is a very deep and profound one. I don't have time to deal with it, but I hope Roger will pick up this theme. I just want to finish on one particular point, because you see headlines like this: could time run backwards, or when time runs backwards? This is absurd on many levels, quite apart from the fact time doesn't run anywhere, as I hope I've been at pains to point out. The idea of time running backwards gives you the image of a clock sort of going anti-clockwise at high speed or something like that. That's not what is intended by this. There is a legitimate point. Could the arrow of time, defined carefully in the manner I have, ever reverse in the future? And that's an old idea, that if the universe should recontract, then one of the arrows of time that Daniel talked about, the expanding universe, would go into reverse. And there's a lot of people have thought, well, if that happens, maybe everything would go into reverse. And the names of some of those people include John Wheeler, Murray Gell-Mann, Jim Hartle, Tommy Gold, Stephen Hawking. You know, these are not. These are eminent people, let's put it that way, and they've all flirted with this idea that time would run backward in a recontracting universe. And they've all retracted. I mean, it turns out that that's just an idea that really doesn't work very well. You could do it, the entropy goes up even when the universe is contracting. You could define it the other way. You could define the future to be to the left. There is a subset of universes where the entropy would go up and come down again, but you'd have to contrive exceedingly special initial conditions for the arrow of time to reverse. It's not impossible, as we heard from the previous lecture. It's there in the laws of physics, but it would be very, very contrived initial conditions. And the final point I want to make is that within the concept of eternal inflation, where our Big Bang is just one of an infinite number of bangs scattered throughout space and time, our universe comes with its arrow of time pointing this way, but the overall eternal inflation, the overall system, the laws are time symmetric, and so there'll be universes with the arrow reversed in the other direction. And so this is another way in which we can envisage a reconciliation between the directionality of processes in our universe, our arrow of time, and the overall time symmetry of the universe. That's it.
That was perfectly on time. You have time for a couple questions?
Okay, thank you for that great talk, Paul. So I have a question about the null cone that you brought up, or the light cone in the special relativity diagram.
Yes.
So, and you say that time is not flowing, but it's about the duration between events.
Yes.
Right. So light traveling through space-time, like from the sun, takes 8 minutes to get here.
Yep.
Those are two events, right? Light leaving the sun, light hitting the earth. But are those events separate for the light? Because the light is traveling along a light cone.
Right. So
could you elaborate on that?
Yes. Yes. So this came up in an earlier question about. It's often expressed, you know, what is the world like for a photon? Everything would happen at once,
right.
Because in its reference frame, the duration between those events is 0. For us, it's 8.5 minutes or something. And there's complete consistency between those because the theory of relativity gives us a way to transform mathematically between the duration between two events in one reference frame and another reference frame. And where you get into difficulties is if you're outside the light cone or the null cone, then of course we have the ambiguity that I was talking about. But within the light cone, the cause and effect relation would be retained. And so nobody would say that, well...
Yes, so would you just say that time does or does not exist for light?
Oh, yeah. Well, you know, that's a philosophical question. So
Is it?
the way
Okay.
the way you deal with it, you can have what's called an affine parameter along the light cone, and I don't know if Roger's listening to this, but he'd be like the world expert on exactly you know how you keep track of what a photon is doing as it goes into the future. But there is a way of capturing that mathematically that
Okay.
is completely consistent with everything I have
Thank you.
said. Okay.
Hey, thank you. That was a really interesting talk. I have more of a theoretical question. I'm going to keep it like kind of brief. So about the notion of time being the distance between events rather than a
Well,
flow.
duration, or distance, yeah.
The delta between like two things, phenomena happening. I think about this in terms of like the psychological aspect of if you're really bored, time, like it seems like nothing happens, but time goes by really slowly. If a lot is happening and you're engaged and entertained, a lot can happen, but it flies by. And this is something that Terence McKenna has talked about, where over the course of time, 1,000 years ago, we could do very little in a chunk of a distance between two discrete events, whereas now with computers, we can achieve infinitely more than we could have in that same distance between two events. And so he's kind of framed this as the notion of time accelerating. And so I'm wondering, with your notion of this arrow of time, what you think about that arrow actually accelerating as opposed to staying static.
Right, so your question would have meaning if the claim is that a particular physical process happened faster. So that we saw this, wonderful mixing experiment. How long did it take to mix? That's how long the entropy took to rise. Well, if we discovered that everything seems to be happening faster than it did 10 years ago, that the mixing process happened faster, then that would be what you're talking about, an acceleration in the arrow of time. There's no evidence for anything like that, but then you have to wonder, if it affected all physical processes, including our mental processes, we wouldn't notice. Just like if you woke up and you were half the size you were yesterday, but the universe and everything around you is half the size, makes no difference. It's only one system relative to another. But the one of the arrow that has been discussed today, where you can actually say that, is the rate of expansion of the universe. That gives you an arrow, and the rate of expansion of the universe has changed over the history of the universe, and we can measure that change. So that particular gauging or measurement of, if you must use the word passage of time, has changed over time. But I don't think any of the others have done.
So it's about the time it takes for the cranberry juice to be poured into the water.
Right. I mean, that's all happened so fast, it's difficult to see. But if you take a slightly slower example, you take a flask of a gas with a membrane down the middle, oxygen on the left, hydrogen on the right, or whatever you want it to be, maybe nitrogen if it's air. Remove the membrane and then wait. After, I don't know how long it would take, but maybe a few seconds, the molecules will intermingle because they're rushing around, and then it will all be mixed up in a smooth state, and you couldn't untangle it again. And that process might take a few seconds to equilibrate, is the term we would use. And then you could imagine somebody claiming, well, all this is happening 3 times as fast now as it did in 1900. Well, you could do the experiment.
Okay, I see what you're saying. Yeah, thank you so much. Appreciate it.
I'm afraid we're going to have to cut it off there. We're out of time. But we're going to leave time for a session at the end. But Sue, you have the first question for the group. I owe you.
Oh.
No, at the end.
What?
At the end. For all three. Let's give Paul Davies a round of applause for a fantastic talk. Thanks, that was great. Okay, our next speaker, remotely from Oxford in the UK, is Sir Roger Penrose, who's well known to people who've been coming to these conferences, as well as most other people in the world, I'd say, or many. He won the Nobel Prize last year for his work on black holes. And there he is, Roger. We see you.
Well, thanks for the opportunity in giving this talk. I want to talk about time in conscious experience. And I was interested to hear that people are beginning to pay attention to the fact that microtubules seem to exhibit quantum effects in connection, and also they can be suppressed by general anesthetics, which is an indication that quantum theory or quantum mechanics has some relevance to consciousness. I should explain that the OR scheme that Stuart, Hameroff, and I have developed really also depends not just on quantum mechanics, but on quantum mechanics, or I almost say where quantum mechanics goes wrong. It's where quantum mechanics is incomplete in the sense that it's the measurement part of quantum mechanics. See, quantum mechanics as it currently exists consists of 2 parts. One is the Schrödinger equation. There's a thing called the quantum state, or the wave function, which is this thing, this red psi I've got here. And the quantum state evolves in time according to the Schrödinger equation. And this describes what quantum mechanics says the universe is doing, if you like. Now, the thing is that when you make a measurement on a system, you change the rules, and you have to adopt another procedure, which is in green here, and it involves a thing called the collapse of the wave function. Now, the collapse of the wave function doesn't follow the Schrödinger equation. And instead of having an evolution of a single thing, it presents you with a probability distribution of a number of alternatives, depending on what parameter you're measuring. You might say this doesn't make much sense if psi is meant to be the description of everything, because the measuring apparatus is just a system, and so why isn't that part of the quantum system? So that's the big conundrum about quantum mechanics. But the way it's used, you have to adopt another procedure, which is this measurement procedure, which is number 2. Now, Stuart and I are adopting a point of view, which is that there is some physics going on which is involved in the collapse of the wave function, which is yet unknown exactly what that is. But it's sometimes called the reduction of the quantum state. And basically, it's when things get big enough. You see, in standard quantum mechanics, if one thing can happen or if another thing can happen, then you can have both things happening at once. This is part of the way that quantum mechanics works. But when you're making a measurement, it's only one thing or another thing. And so we call it OR, which is the objective reduction of the quantum state. It also spells OR because it's one thing or the other. So we bear that in mind, that that's really what we're using. And we consider that consciousness is really this physical process, the objective reduction of the state, objective reduction, the OR, but orchestrated in some way, which is the ORC part of ORC-OR. And that, of course, is not something that we know in detail how that works, but somehow the state gets reduced in order. I mean, you wouldn't have physics as we know it if that didn't happen. You would have these superpositions all over the place, which you don't see. Okay, so that's the point I want to make. Now, here I want to say, well, you might say, well, the measurements are now, observations are now indicating that quantum mechanics has some relevance to consciousness in connection with microtubules, apparently. And if we're trying to look for observations or experiments which go beyond current quantum mechanics, that's sounds like a hugely tall order. I mean, we have indications that quantum mechanics as we know it, but how about something beyond quantum mechanics? Do we have any experiments of that nature? Well, I'm claiming that there is an experiment which isn't directly showing that, but which seems to be consistent with the picture that I want to present in this talk. And this experiment was something done in the late 1990s, I think, by Benjamin Libet and some others. And he did an experiment. I wouldn't be surprised if they weren't illegal these days, I don't know. But these were experiments done on patients who had to have an operation on the brain for some other reason. And Benjamin Libet, would take the opportunity to perform these very interesting experiments with the patient's consent, of course, which had nothing to do with what the operation was for. And this particular experiment had to do with, well, the patient would have a finger which would be stimulated electrically, very gentle electrical stimulation, which would be felt by the patient, or there would be a stimulation of that part of the brain, in the sensory part of the brain, which would be just the same part, which would be just sensitive to just the same part that the finger would be stimulated. So normally, the stimulation of the finger would be accompanied by that part of the brain being activated. So if Libet would stimulate with an electrode, very gentle current at that part of the brain, the patient would feel the finger, that very same finger, being stimulated. It wouldn't be quite the same feeling, so the patient would be able to distinguish one from the other, but it would be definitely felt as though that finger was being stimulated. Okay, now the first experiment, there are several in this picture. It's actually from a picture that I had in The Emperor's New Mind. So I described this experiment there before I knew Stuart, and this was the conundrum which is presented in this experiment, as I mentioned. So the first line right at the top is where the finger is stimulated, and I must just check that I'm talking about the right one here. When the finger is stimulated and the patient feels almost at once, you see the line at the top is the stimulation, and the mark just at the bottom is the patient feeling something. So almost immediately after the stimulation, the patient would feel something. Now, when I say almost at once afterwards, how would you know when this was? Well, there is a clock, a fast-moving clock in the room, which the patient would see, and the patient would see exactly where the hand was at the moment that patient was feeling the stimulation. So that was pretty well the same time. I mean, a very, very minuscule delay, but hardly any. And that's the top line now. Now, the next line is if the brain stimulation takes place, then the patient, and that's the wiggly line there, the brain stimulation takes place, and the patient doesn't feel anything until, if we go down to the third line, until about half a second later, and then the patient starts to feel something. It feels like the finger being stimulated, but not quite the same. The patient can easily distinguish one from the other, but it feels as though something's happening to that finger. And that's the wiggly line underneath, which is indicating that. Okay, now the next horizontal line, we have the finger stimulation. I have it right, I'll look at my picture again. Finger stimulation first. No, there's no, yes, there's no, make sure I'm looking at the right line here. The brain stimulation goes along, and then a half a second later, the patient feels something. The next line, yes, sorry. The next line is D. The finger is first stimulated, then the brain is stimulated about a quarter of a second later. And nothing is felt about the actual stimulation of the finger, which is very strange, because if the brain hadn't been stimulated, the finger would have been felt by then as having been stimulated. The strange thing is that when the brain being stimulated at that part, the same part which is to do with the sensation of the finger being stimulated, it seems to cancel out what would have been a sensation of the finger being stimulated. Eventually, when the brain stimulation goes for long enough, half a second, the patient begins to feel the brain stimulation of the finger, but never the actual finger stimulation, which is strange. The one before is the one right at the bottom, the horizontal line, is the brain stimulation goes first, and then the finger stimulation, and the finger stimulation is felt more or less immediately afterwards. And then the brain finishes. This one looks logical again. You see, the brain stimulation is felt about half a second later. So that one looks sort of logical. The one that looks strange is the one above it, when the brain stimulation simply not felt once the quarter of a second later, the brain is being stimulated. Now, I don't know that people comment on this very much. They comment on other experiments done by Benjamin Libet, but this one seemed really puzzling. And I did, in The Emperor's New Mind, I did make some suggestion, not very forcefully, that perhaps there is some delay in when the brain actually feels, when you actually feel the stimulation. It may be delayed by half a second or something like that. But I couldn't quite make sense of that, and I didn't make the point very strongly. Okay, well, let's move on. These are two well-known characters. The one on the left is Einstein, who had a big influence on things I've done. The one on the right is not so well known, but he has also had a big effect on what I've done, namely Gödel. This is Kurt Gödel. They're both at Princeton at the same time. And Kurt Gödel had proved a remarkable result, which I found very striking. The question here has to do with whether, when we know mathematical truth, we are using some algorithm in our heads. That's the sort of point that's coming about. Now, if that is an algorithm, which I'm calling R is meant to be some rules that you maybe have built into your brain somehow, but it doesn't have to be that. It's just some set of rules. that allow you to prove mathematical theorems. And if you follow the rules of R, you might get a proof. I'm sorry, R is I hope I'm saying it right. Is that R are the rules, that's right. There is a statement which Gödel constructs out of the rules. He just looks at the rules and builds up a mathematical statement, which is this thing G of R. And what Gödel shows that if you believe that R only gives you truths, then you must believe that G of R is also true. However, the way Gödel constructs it, you can see the way it's constructed, that G of R is not provable by the rules. It's a clever thing which actually states that it's not provable in some sense by the rules. And its statement, you see, if what it says is false, that it's not provable by the rules, then it is provable by the rules, and therefore it's true. If it's not provable by the rules, then what it says is true, and therefore it's true. If it is provable by the rules, then it has to be true by the rules. So it's true other way around. But it's true, but not provable by the rules, because if it's true, you just follow the logic, and it shows you that it's true, but not provable by the rules. Now, how do you know it's true? This is what puzzled me. How do you know it's true? Well, you only know it's true because of your trust in the rules. And why do you have trust in the rules? Because you've looked carefully at the rules and you believe, okay, those rules only state things which are completely obviously correct. And that if you just follow those rules, everything you get following them must be true. But what it tells you is that your trust in the rules, if you like, your belief that the rules only give you truths, transcends the rules themselves. Now, I found this amazing because it tells you that you can't, any rules you could understand can't be rules that govern your understanding, because the Gödel's theorem gives you something outside that. Of course, it might be that we have rules in our head which are so complicated that we can't possibly know them in some sense. So the next thing, I won't go into this, but it's the thing called Goodstein's theorem, which I've given in other lectures. But it's a very nice example, which shows you something which can't be proved using the ordinary rules of arithmetic that you learn at school. Nevertheless, it's true. And you can show it's true and not provable by the rules of arithmetic. That was shown by Paris and Kirby. That was a theorem they showed, that Goodstein's theorem cannot be proved that way, even though it's true. And how do you know it's true? You know it's true by some procedure, which is known as the transfinite arithmetic. And the point I want to make here is that how could one know that's true if the algorithm in our heads, if it is an algorithm, how could it have arisen by natural selection? And here I have a sort of cartoon of what natural selection might do. People building a mammoth trap. Okay, you can see it has some benefit. People in the distance domesticating animals, building shelters, growing crops, doing all these things which are useful and could have been by developing human understanding in general ways. In the front, we have a mathematician trying to prove some theorem, and he's just about to be pounced upon by this saber-toothed tiger. Clearly, that doesn't, for our ancestors, have any particular, certainly not the kind of thing in the Goodstein theorem. That's way beyond anything which could have had any kind of selective advantage. Now, how do we know it's true? We know it's true because of some wonderful thing that this is Georg Cantor, who really established theorems about infinite numbers, and people have never done that before. It was really a remarkable thing. And he shows you could do perfectly good mathematics with infinities and different kinds of infinities. And he developed techniques which could prove the Goodstein's theorem. It's completely easy to prove once you know these Cantor's procedures. And the remarkable thing is, I'm saying you don't need to have the genius of Cantor. You just have to understand what he was doing. You just have to read the way he thought, how he proceeded, and you can see, oh yeah, that's fine, it works. Now, how do you know it works? By natural selection. It just seemed to me quite beyond any kind of algorithm in your head. So there's something beyond algorithms, and what could that be is the mystery. Here we have the next person I want to feature is Alan Turing, and here he talks about the idea of things that you can't do by algorithms, just to show that algorithms are not everything. This is an example. I don't think he knew this particular example, but it's a nice example that I made up, which depends on certain theorems where you know that there is no algorithm. Now, what there is no algorithm for is whether or not, if you have a finite set of what are called polyominoes, here I have 3 of them on the left, they're made of equal sized squares stuck together along their edges, a plane shape, and I've got 3 different ones. There are 3 different polyominoes. And the question is, can you assemble these just using these shapes? Can you cover the entire Euclidean plane? And here I've just shown you a way you can do it. You can indeed, in this example, cover the entire Euclidean plane, but not in a way which ever repeats itself. Now, the point about this is that because of such examples like this, it can be shown there is no general algorithm for telling you whether a set of things can tile the whole plane. I'm just showing you examples for which there's no general algorithm. Here's another example where you've got shapes like this. I just want to show you how difficult these problems can be. Here you have a regular dodecagon, a regular hexagon, and a regular square. And if you just had those without any markings, you could certainly use this pattern to cover the whole plane. And that's what I mean. But now I want you to fill these things by rotating the shapes in certain ways that the patterns match. And can you do that? The answer is yes, you can with the shapes I've given you, but it never repeats itself again, and you get patterns, very complicated ones like this. Joshua, a friend of mine who actually produced this pattern. It just shows you how very, very complicated it is. The dodecagons would be very small, like these little rings in the middle here, and this would use quite a lot of them. I'd like to see putting it on a computer, how far it would actually get. It would be intriguing. If you know how it's done, then you can put it on I mean, this was done by computer, but that was knowing how the pattern was built up. And that was how it was done. Anyway, I just wanted to go back now. You see, is there a way in which something non-computable could come about in physics? And I don't see any role for that in standard classical physics, even general relativity. I didn't know at the time how well computers could work general relativity, but they do now, and you can work out how black holes or neutron stars can spiral around each other and produce gravitational wave signals. And these signals, the very closely worked out shapes, can be analyzed and observed in LIGO. This is a gravitational wave detector. So this is just showing you how well it is possible to put calculations in general relativity on computers. It can be very difficult to do, but you can do it. What about classical Newtonian mechanics? Yeah, sure. What about Schrodinger's equation? Well, you see, that goes back to the quantum mechanics, Schrodinger's equation. You can certainly put Schrodinger's equation. Now, there is a little point about this, because calculations involve discrete numbers, and you've got to make sure that approximating continuous parameters by discrete numbers doesn't give you some little catch to this argument. There is a point which might give you a catch. I think that's worth exploring. I don't know the answer to that, but I don't think that is the answer. I think the answer is much more likely to be here. You have the answer, namely that either you have quantum mechanics behaving according to the Schrodinger equation, or this mysterious collapse of the wave function, which is not understood. And the argument that I was making was that it's got to be in number 2. Whatever it is that in our brains makes us do things beyond a computer, which makes us able to do non-computable things. And the argument about non-computable things goes back to the Gödel theorem and all that. They're part of the argument I was giving you. And that is the claim, that there's got to be something dependent, just not on quantum mechanics, so it goes beyond that, but beyond quantum mechanics, but beyond quantum mechanics, in whatever is going on behind the scenes in the collapse of the wave function, or OR, objective reduction, and have to be orchestrated in some way that the brain could make use of it in a useful way. Now, I'll go on to the next slide, which this is just to show you, jumps to what I don't want yet, the basic principle behind general relativity, which is the principle of equivalence. It's the same thing which Galileo described. If somebody dropped a big rock and a little rock from the Leaning Tower of Pisa, they would drop together. And an insect sitting on the big rock looking at the little rock would think that there is no gravity. Of course, when they hit the ground, that's another story. But as they're falling, you've managed to cancel gravity out. And this can be happening on the big scale too. Here we have a futuristic 2001 type space station and an astronaut, and that astronaut is far enough. Well, the Earth is right there, so the Earth's gravitational field, you might think, should play a role in what the astronaut feels. But so long as the astronaut is considered small enough and is moving in orbit, then the astronaut will not feel the gravitational attraction of the Earth. And this is the principle of equivalence. It's a very basic principle of general relativity. It's the foundation stone of Einstein's theory. And the remarkable thing is, this foundation stone of Einstein's theory is in conflict with the foundation stone of quantum mechanics. Now, what do I say the quantum foundation stone of quantum mechanics is really? It's the principle of superposition. That is to say, if you have a quantum thing and it can do one thing, or if it can do another thing, then it can do the one thing and the other thing at the same time. It's called quantum linear superposition, and the rules of quantum mechanics simply say that. The Schrödinger equation, if you've got one solution and another solution, you can add the two solutions together and you get a third solution. Or you can multiply one solution by a complex number and the other one by a different complex number, and you get a new wave function, which is still a solution of the Schrödinger equation. So those are those two principles, the principle of equivalence and the principle of linear superposition. And I maintain that they are in conflict. And the way I was thinking about this is you think of an experiment being done on a tabletop where you want to take into consideration the Earth's gravitational field. I won't go into the details here, but there's a green coordinates and purple coordinates. And one of them is doing it Einstein's way and the other is doing it Newton's way. Newton's way would be, say, consider there's another force, which is the gravitational force. In quantum mechanics, they do what's called putting another term in the Hamiltonian, the straightforward procedure. The other point of view, which is, no, you take your coordinates freely falling, and then there is no gravitational force. They should give you the same answer because the principle of equivalence says they're the same. You go through the quantum mechanics and you find they're almost the same. Almost, because the green one is one of the Newtonian wave function and the purple one is the Einsteinian wave function. And you see they're almost the same. They just differ by this thing called a phase factor. And you would normally say a phase factor doesn't make any difference. You're working out probabilities and the phase factor just cancels out. However, you look carefully at the phase factor and you see in detail, it's got a term in it, which tells you that your two wave functions are in different vacua. So if you're doing quantum field theory, you're actually cheating when you make a superposition, because this vacuum for this one is a different one for that. And one of the rules is quantum field theory is you can't superpose two different vacua. That's cheating. So you're stuck. So what do? I'm stuck here. What do, I sort of make a kind of, I say, I agree I'm stuck, but let's cheat a little bit, which is to work out this sort of error involved in making the superposition. And you look at it and you do a little bit of fiddling with the mathematics, and you come out with this thing called E sub G, which is a measure of the uncertainty of the energy in this superposed system. Now, the point about that is when you have an uncertainty in an energy, that is related to a lifetime in the system. This is a standard thing in unstable particles, that you have an energy uncertainty is related to a lifetime of the system. So that I'm using that thing sort of rather backwards from the way it's normally used, but nevertheless, it's the same kind of argument. So you say that this system of the superposition has a lifetime, whose lifetime is roughly speaking, the reciprocal of this energy uncertainty with the H cross in the numerator. Now, this formula for the lifetime was found independently and earlier than I did by different arguments by Lajos Dioschi. And the conclusion one can come to is written down here. The lifetime of a system is given by this thing at the top here, is h bar or h cross, that's the Dirac form of the Planck's constant, divided by this energy uncertainty. And that gives you, and you can identify this energy uncertainty as the gravitational self-energy of the difference between the two mass distributions. You count one of it positively and the other one negatively and work out this thing called the gravitational self-energy. It's also, for a straight translational motion, the same as saying, if you imagine two lumps on top of each other of this energy and you pull them apart, how much energy would that just cost you if it's only thinking about gravity, no other forces, just gravity? That's the same thing. So that gives you some feeling for it. It's a very small quantity, but can be quite big if you're thinking about quantum systems. And certainly the lifetime, if it was anything of a sort of sizable quantum thing, that lifetime could be extremely short. Anyway, that is the formula for the lifetime, which is sometimes called the Dioschi-Penrose model. I wanted to say something, though. Some experiments were performed. There is a thing that people deduce from this lifetime. Let me see if I can, I'm not sure it's the next picture. No, it's not. You see, if you imagine an object, it could be just a lump of rock or something like this, an object of some sort, there are many, many atoms in that. And they might involve this criterion taking place from time to time within that lump. And so when that happens, a superposition in that lump, the atoms would start becoming suddenly not just in two locations at once, but one location. And it's a bit like something heating. So that the argument is that there would be a heating of an object because of this collapsing taking place all the way through it. And this is a sort of argument which is reasonable argument if you assume that the collapse is like any kind of motion of particles. But anyway, people have done experiments and taken lumps of stuff down mines, and they have never found this heating effect. So it doesn't seem to be there. And in fact, they've argued that this disproves the Dioschi-Penrose model. Well, you see, what I want to say is what it does disprove is the heating. But the heating is not something which I believe should happen. I'll come to that in just a minute. Just before going to that, though, I should mention that I was writing about some of these things in The Emperor's New Mind. Some of these things go beyond what I had in The Emperor's New Mind. But I was hoping that young people might be stimulated by my book. Most of the people who wrote to me were retired old people, which was a bit of a disappointment, but still, some people were reading it. What was more exciting to me was that Stuart Hameroff read my book, and he wrote back to me and said, "You evidently aren't aware of these things that are called microtubules." I'd known about the sort of standard Hodgkin-Huxley transmission of nerve signals, and it didn't seem to me there was any hope of preserving coherence in such nerve signals. They just propagate into the environment, and there's no way of keeping things from environmental decoherence. There's no hope, I thought. But when Stuart mentioned about the microtubules, I thought, wow, this is a much better chance. And I liked also the symmetry of the structure, which is a promising feature too. So we got together and we developed this OR scheme. Some of the model got changed from what it was there. But anyway, it did seem promising. And the fact that microtubules seem to be behaving quantum mechanically is very exciting, this new information. But let's get back to the state reduction, because here is what I'm drawing. This is a space-time picture, time going up the picture. So it's a bit like in the previous couple of lectures, people were talking about space-time pictures. Time is going up the picture. I'm imagining a body which now is put into a superposition, quantum superposition of two different locations. They spread out quite a long way distance. And then it gets to this criterion, the Dioschi criterion, and one of them collapses to be the whole. Well, see, one of them disappears and the other one becomes the whole story. Now, this presents a difficulty with relativity. You see, what are these lines I've drawn here, these angled lines? Those represent simultaneous with regard to a rapidly moving observer. The picture is drawn with respect to an observer stationary with the objects initially. But what about with respect to a moving observer? You would have the simultaneous lines would be tilted with respect to the horizontally drawn lines for the observer in the frame of the initial particle. But why should we use that frame? We should be using any old frame. So if you use one of the other frames and you use it right up at the top of the picture, you see in one case, the particle has disappeared before the state has actually become the other one. And that doesn't make any sense because you could have a measurement which has a probability of finding it in both places at once, or no places at once. One observer could make one of them disappear and the other one also disappear because before it's become entirely there, it has an amplitude of being there. And so the rules would tell you that it still might disappear. And so they might both disappear. That was the T one's tilted this way and the S one's tilted the other way. It could be that they're both there at once. This one hasn't quite gone by the time this one has become everything. And it doesn't make any sense. The way that one used the rules of quantum mechanics simply doesn't work. There are ways of making it almost work, and you can see using other arguments, which I won't give you here, that it really doesn't work. So the only way to make it work is to say that the reality goes back to the initial point. Now here is where you have to say what you mean by reality. And the argument is that you have to have two kinds of reality. One reality is what I call classical reality, and the other is what I call quantum reality. Now, it took me a long time to realize you needed these two types of reality. Classical reality is the normal kind of reality where you can ask a system what it's like. For example, if you have say a jar, empty jar of honey or something like that, and you want to ask what shape it is, you can ask, you say, what shape is the rim of the top? What shape is the sort of thing? What kind of symmetry has it got? And so on. And so it's a perfectly good question, and then it can ask, because my shape or my state is X. You can say, what is your state? And it can say, my state is X. That is nice classical reality. Now, what about quantum reality? Now, in quantum reality, I'm using the thing I call Einstein's dictum. He was asking this question, is the quantum state real? And there is a sense in which it is real, because you can ask a certain question. If you think you know pretty well what it's like, then you can check up on this. Suppose you've got a good theory which tells you the state ought to be X. Then you can say, is your state by any chance, is it X? And the state can say, yes, my state is X with certainty. So you could repeat this experiment many, many times. Each time, if you get the right, you think you know what the answer is, and it says, yes, that's right, with certainty. And that gives it what Einstein called an element of reality. But it's strangely a different kind of reality. This is the quantum reality. And there's a way of distinguishing quite nicely when you think of a spin half particle. I don't think I want to go into that now, but you can quite easily see the difference between classical and quantum reality. Classical is a much more robust kind of reality, but quantum reality seems to be a kind of reality. It's really there. It's just that it's hard to check up on what it is. If you have a good theory, what you think it should be, then you can check it. And if the theory is a good theory, it will tell you the right answer. Anyway, so let me move on. And I don't need to go into the details here. This is actually a nice example called an EPR, or Einstein-Podolsky-Rosen experiment, where you have say two protons and they start off in a spin zero state. And you each, Alice over here and Bob over here, these are world lines again, time going up the picture. And at one point, Alice makes an observation on the state. And at another time, Bob makes an observation. And the quantum reality goes backwards in time in this curious way along the past light cone. The whole thing is completely consistent, even though very strange. So the quantum reality is consistent over the whole picture, even though it has this curious backwards propagation rule. You can't send a signal backwards, that's clear. because quantum reality is pretty constricted about what you can use for signaling. And that's a really important point about it. I want really to concentrate on the last picture here. I think it's my last picture, which is, well, it's the last picture, except for going back to that. This now is a space-time picture. This sort of sheet here, it's got a little kink in it because there is a rock or some massive stone here, sitting here, which is causing a depression in the space-time. So the space-time you see is the sheet here with a little kink in it. Now, as time progresses, that kink goes up as this rock remains there. Now, what we have here is a beam splitter, that's a half-silvered mirror, and a laser shooting a very high-energy photon. This photon, the beam splitter acts so it half transmits and half reflects. So half of the photon's wave function gets reflected downwards, half of it gets transmitted horizontally. So that the rock is in a state of half being hit and half being not hit. If it's being hit, it will slightly move and move and move and move. If it's not hit, it will stay put, or whatever it is, and you follow the history upwards, and you see the space-time starts to bifurcate. It becomes two different sheets of the space-time. There comes a point when the Diochy criterion comes in, and you say it becomes one or the other. And then you say, well, what about the superposition? Well, according to the criterion that I've just been saying, it's got to go right back to where it was before it bifurcated. And the classical reality followed this one sheet. It's as though it never bifurcated at all. It was all the time, this classical reality was that sheet, which is quite a strange picture of reality, but it seems that for the classical reality, you've got to do it this way to make sense of it. The quantum reality is allowed to be this rather strange superposition, and consciousness, according to the OR scheme, would be sort of hanging around up here, and maybe it's making a decision of some sort as to which branch it should have been earlier. So that's an interesting question. And it relates to the limit experiment, because now we're using the passive aspect of consciousness, whether the sensation is somehow retroactive. And Stuart has this model where it doesn't happen until you reach the pyramidal cells, which are not quite the uppermost layer of the cerebrum, but they're not present in cerebellum. So it would be consistent with them being a key part of the conscious process. But it may take a long time for a signal to get up there. But the argument is that these things are kept in superposition, and that the reduction of the state happens later on. And when you're looking at the clock, say when the patient is looking at the clock, this is delayed also, and so that the patient thinks it's simultaneous pretty well with the stimulation of the finger, but in actual fact, this is happening something up to maybe something like half a second later, which is rather extraordinary. Now, the question is, how can you make use of that? Is Roger Federer, when he's deciding to go down the line rather than cross-court, actually consciously making that decision? Well, it's still possible, provided these two alternatives wouldn't be with muscle superpositions, but there would have to be still some choice about which is actually the action which takes place is still in a quantum superposition. And that quantum superposition is allowed to be resolved to be one or the other, in a sense, retroactively. And so that you can have what seems to be a faster than light action. I also wondered whether this might relate to other things, like you have stories when people maybe fall off, say, off a high balcony or something, and think they're going to die, and they don't, because they fall into something comfortable. I don't know what it is, but somehow they survive such falls. There are examples where people, and they have this impression that their life flashes before them as they were falling, and it doesn't seem to have been enough time when they fall for all these experiences to have happened. Well, I'm just suggesting, it's only a suggestion, not even anything more than that. Maybe in such situations, there might be a feeling that these thoughts happened afterwards and were felt to be earlier because of this backwards referral. And it wasn't when the person was falling, but actually only later when there was enough time to think through these events which happened during the person's life. I have no idea really, but you can at least, there's another sort of thing that one might imagine. So it would be very interesting to have experiments of this nature to test whether this kind of retroactiveness in sensations is something that's really going on. And I really think that would be very useful to see whether something like this is involved. Anyway, thank you very much.